Hello everyone. As in the last series of the lecture regarding complexometry, we were discussing the properties of an indicator used in EDTA titrations, and we had said that the metal indicator complex should be weaker than the metal EDTA complex for a complexometric titration reaction to proceed. The types of metal indicators which can be used in complexometric titrations. An indicator is a substance that gives a notable color change towards the end point, that is the completion of a reaction. So, this is how we define an indicator. Indicator may be of various types depending upon their role. In EDTA titrations, the indicators which are used are metal indicators which form complexes with metal ions. For example, eriochrome black tea, also called solochrome black tea. It is an azo dye having the following structure. This is the structure of eriochrome black tea or EBT as we say in the short form. As we can see, there is one sulfonic group which is always in the ionized form, and there are two dissociable protons of the phenolic groups. They are required as and when they are dissociated. Eriochrome black tea or EBT is available commercially under the trade names solochrome black tea, TS, WDFA, chromogen black tea or chrome tea. It is a black powdery substance with a slight metallic luster. Its solution, though, can be prepared in sulfuric acid and water, but it is unstable and decomposed after some time. Hence, for the titration, solid form of the indicator is preferred, wherein its mixture is made with an inert substance like sodium chloride. And this mixture is preferred with sodium chloride because a very small amount of indicator will give a very dark color with the metal. So, as the indicator is added to the metal ion solution, the indicator gives a very dark color, and towards the end point the color change will not be clearly observable, because color changes are clearly observable only in light colored solutions. Another indicator which is a metal indicator is calmagite, which is a metal indicator and an azo dye just like EBT. The structure of calmagite is as shown in the adjoining figure. The advantages of using calmagite as an indicator over EBT is that its solution is stable and does not decompose on storing. So, instead of a solid solution, an aqueous solution of calmagite can be made containing few drops of a buffer of pH 10. Coming back to eriochrome black tea or EBT, EBT has both acid base as well as metallic properties. EBT as an acid base indicator, the sulfonic group in EBT can be assumed as completely dissociated within the acidity range of EDTA, as we have seen in the structure earlier, wherein one sulfonic group is along with a negative sign, assuming that it is completely dissociated. According to the changes in pH, the two phenolic hydrogens in EBT are dissociated, and the dissociation of these is accompanied by color changes which are characteristic of the indicator. So, this is how the reaction representing the changes in the indicator is shown. H2F negative is the indicator wherein two phenolic hydrogens are attached to the EBT indicator as seen in the structure earlier, and when the two phenolic hydrogens are attached to the indicator, the color of the indicator is red. At a pH range within 6 to 8, one of the hydrogens or the phenolic hydrogens gets dissociated to give the blue color of the indicator, showing the structure as HF2 negative. Beyond pH 10, around pH 12, all the two hydrogens of the phenolic group are dissociated to give F3 negative, which is the representation of EBT without the two phenolic hydrogens. So, the 3 negative charges stands for one dissociable hydrogen, another dissociable hydrogen, and one negative charge already present on the sulfonic group. EBT also behaves as a metallochrome indicator. Depending upon the pH of the solution, EBT can occur in 3 different colored forms. However, in EDTA titrations, only the blue form of the indicator is needed, since the pH of EDTA titrations is maintained at 10. The complex of EBT with metal ions is red, whereas the free form of EBT is blue, which forms the basis for EDTA titrations. That means the color change in EDTA titrations with EBT as the indicator is from red to blue. When the mixture of metal ion and EBT is taken in a titration flask along with a buffer solution of pH 10, and this buffer is generally an ammonium chloride solution, the color of the solution is red. When this solution is titrated with EDTA, the metal EBT complex or the metal indicator complex, which is red in color, is replaced by the metal EDTA complex, which is colorless. So, the point to be noted here is that the color change red to blue is due to the formation of the metal indicator complex, that is giving a red color, and the blue color is due to the free indicator after the titration is complete. The metal EDTA complex, however, is colorless. So, this is the reaction which is showing the changes occurring. The metal indicator complex or the metal EBT complex on titration with EDTA forms metal EDTA complex, and EBT is set free in the solution, and this process takes place only when we know that the metal EDTA complex has a higher stability constant than the metal indicator complex. Hence, this particular reaction can proceed. Blocking of the indicator. Not all metal ion complexes with EBT can be broken by EDTA to form the metal EDTA complex, and hence not all kind of reactions can proceed towards completion. Metals like aluminium, copper, manganese and nickel cannot be estimated complexometrically using EBT as the indicator. However, there are other methods to estimate these ions complexometrically. A strong complex formed between these metal ions and EBT prevents the possibility of titration of these metal ions with EDTA. So, no matter how much amount of EDTA is added to the metal indicator solution, the metal indicator solution does not break, and hence the titration does not proceed. This is called blocking or poisoning of the indicator. The estimation of any other metal ions in presence of the above metal ions is not possible, since these metal ions tend to block the indicator by forming a strong complex with them. So, along with aluminium, if another metal ion is present, then that particular metal ion, say calcium, will not be able to determine by EDTA titration, because the indicator EBT will form such a strong complex with aluminium that no indicator will be left free to form a complex with calcium, and hence calcium will not be estimated in presence of aluminium using EBT as the indicator. So, considering aluminium as the metal to discuss the blocking of the indicator, aluminium forms a strong complex with EBT, and thus direct titration with EDTA is not possible. Hence, titration of any other metal in presence of aluminium is not possible, and aluminium will have to be masked in order to let the reaction happen. Similarly, in the case of copper, the stability constant values of copper EBT and copper EDTA complex are very similar. Hence, the formation of copper EBT complex will be as easy as the formation of copper EDTA complex. So, the reaction will shift from one complex to another. The rate of reaction will thus be very slow and EBT will be blocked by traces of copper in the solution. However, the reaction can take place in presence of copper if it is masked by forming its cyanide complex, as can be seen by the following reaction, where tetramine of copper is reacting with a cyanide solution in the form of either potassium cyanide or sodium cyanide, wherein copper cyanide solution is being formed and copper now is considered as unreactive, or it is complexed with cyanide, or it is masked in this manner and will not interfere in the titration of any other metal if two metals are present together, that is along with copper another metal is also present, and that has to be estimated. So, in this particular reaction, copper is reduced to its copper 1 or cuprous cyano complex, which is unreactive, thus masking copper. Since a reducing agent is present during this conversion, the oxidation of the indicator is prevented and the blue color is obtained immediately. And this reducing agent is cuprous 1 cyano complex, which has been masked. Manganese can also block the EBT indicator. So, manganese 2 ions in solution oxidize to manganese 4 in the presence of buffer and block the indicator. The addition of a reducing agent in presence of manganese eliminates the problem of the blocking of the indicator due to oxidation of manganese. The reducing agent which can be used here is ascorbic acid. Nickel is another ion which can block the indicator, that is iriochrome black tea. Nickel is very slow in its complexation reactions. Nickel forms a very strong complex with EBT which does not break no matter how much amount of EDTA is added. Hence, nickel cannot be estimated complexometrically using EBT as the indicator. So, if we talk about EBT as the indicator, then this indicator can be blocked by a number of metal ions as we have just seen. So, what is the alternative? The alternative is choosing another indicator which can work in the presence of these metal ions also. And the example of such an indicator is muroxide. The structure of muroxide is as shown. Muroxide forms colored complexes with many metal ions. Free muroxide is violet in color in ammoniacal solution, that means in alkaline solution. Just like EBT, muroxide aqueous solutions are also unstable. So, either freshly prepared solutions or solid solutions or solid dilutions as they are called are used. Muroxide can be used as an indicator for the estimation of nickel ions, calcium ions, copper ions and magnesium ions. Muroxide gives different colored complexes with different metal ions, which changes upon titration with EDTA towards the end point. Another indicator which can be used is PAN. PAN is 1,2-pyridyl azo 2-naphthol and its structure shown is in the adjoining figure. PAN as an indicator is a brick red substance insoluble in water. It is, however, soluble in alkali, ammonia and organic solvents. PAN gives a slight color change from yellow to orange at pH of 8. The reaction of metal pan complexes with EDTA is very slow. So the titrations are done in boiling solution. That is, when pan is used as an indicator for metal titrations, then these metal solutions have to be first boiled to increase the rate of reaction in this case. The most important metal for which pan serves as an indicator is copper. The reaction between copper and pan is very sensitive. As we have seen earlier, copper cannot be estimated using ammonia as the complexing agent, although copper forms a very good tetramine complex, because of the fact that copper and ammonia are proceeding for a complex formation in a stepwise manner, and hence the reaction becomes very slow. So for such kind of titrations, the reactions must be fast enough with EDTA also. So in that case, copper can be estimated using pan as the indicator, wherein copper pan and copper EDTA follow a single step reaction. Many other metals like cobalt, zinc, lead, bismuth and cadmium also formed colored complexes with pan, and therefore pan can be used as an indicator for estimation of these particular metal ions with EDTA. However, many of these metal ions show very slow reactions with pan, and pan is blocked by nickel since the reaction is very slow with EDTA. Another kind of indicator which can be used is pyrocatechol violet, which has the following structure, and in all the indicator structures we have seen that there are phenolic hydrogens which are present, which are easily dissociable and allow the reaction to proceed easily. That is, the replacement with EDTA proceeds easily in this case. Pyrocatechol violet is an indicator which also has acid base properties, and the color of the solution changes with the pH. That is, below pH 1.5 the color of the indicator is red. Between pH 2 to 6 the color is yellow. Above pH 6 the color is violet, and above pH 9 the color is purple. So the color of the indicator changes from red, yellow, violet, purple from acidic to basic or alkaline solution. Pyrocatechol violet forms blue colored complexes in acidic medium and ammoniacal medium with many metal ions. So if metal complexes with pyrocatechol violet, then the color of the metal indicator becomes blue. The earlier colors which are seen are the individual colors of the indicator, that is, without the metal ion, pyrocatechol violet changes color according to the pH. Bismuth is a metal ion which can form a very good complex with pyrocatechol violet and can be titrated with EDTA in acidic medium. The color change in acidic medium from blue to yellow is very sharp. Nickel or copper can also be estimated by pyrocatechol violet as the indicator. Ascorbic acid is added to a solution of the indicator to prevent its aerial oxidation. Ascorbic acid is a good reducing agent. Pyrocatechol violet can oxidize by absorbing oxygen from the air, and hence this needs to be prevented by the addition of ascorbic acid. Pyrocatechol violet has advantage over the indicator EBT. This indicator is not blocked by ions like nickel or copper, whereas in the EBT is blocked by such ions. Again, to the category of these metal indicators, another example is xylenol orange. Xylenol orange is a red brown powder which is readily soluble in water, and the adjoining figure gives the structure of xylenol orange. It is synthesized using cresol red and aminoacidic acid groups via the Mannich reaction, or as we call the Mannich condensation. This indicator has acid base properties, which is yellow in acidic medium and about pH 6, that is slightly alkaline medium, the color changes to violet. At pH 6 the medium is not totally acidic, but a very weak acid, almost towards neutral or alkaline solution. The metal complexes are red or violet with xylenol orange. The color change towards the end point with EDTA is from red or violet to yellow. That is, the metal indicator complex, the metal xylenol orange complex is red, whereas the metal EDTA complex is yellow. The complex formation with certain metal ions occurs in extremely acidic solutions. Now, after we have completed with the discussion of indicators which are used in EDTA titrations, we now need to know that EDTA titrations are selective and their selectivity is bit low. This can be seen by the fact that about 30 common metal ions can be titrated by EDTA. That means EDTA can complex with a number of metal ions, and this is because of the fact that EDTA is a hexadentate ligand and can form complexes easily with many metal ions. Apart from these, all rare earths and some actinides can also be titrated with EDTA by direct or indirect methods. The selectivity of EDTA titrations can be increased or enhanced. For this, metals having different stability constants can be chosen and can be titrated in presence of each other. Coming to those metal ions which tend to interfere in titrations with EDTA, for them masking or screening needs to be done to prevent their interference in titrations. These have to be removed before the titration. Since physical removal of a metal ion from a solution is not possible, so a masking agent is added to prevent the reaction of one substance with another substance. Demasking is a process where the prevention of the action of a masking reagent by a further reagent is done. Masking may be carried out by the following methods. The first one is the adjustment of pH. If the pH of the solution is lowered, then the metal EDTA complex dissociates fully. Following this, another metal which has a stable complex with EDTA can be titrated. Another method of masking of metal ions is complex formation. If there is a solution of two metal ions and is treated with a reagent wherein one of them forms a stable complex with the reagent and the other one does not, then the difference of the two stability constants increases and a selective titration can be carried out. For example, metals like zinc, copper and nickel form suitable cyano-complexes. Cyano-complexes of lead and manganese, however, are weak. Calcium and magnesium do not form cyano-complexes. Hence, in the presence of either nickel or copper, the latter metals, that is lead, manganese, calcium and magnesium, can be treated with EDTA when nickel and copper are masked as their cyanocomplexes. Later on, after the completion of the titration, zinc can be effectively demasked by formaldehyde. That means zinc can be recovered later on by the addition of formaldehyde. For masking aluminium triethanolamine and for masking mercuric ions in solution, potassium iodide can be used respectively, wherein mercuric ions form their complexes with iodide and mercuric iodide is formed, which is remaining in the solution as in the unreactive form, and similarly aluminium forms a complex with triethanolamine which remains in the solution as in the unreactive form. Another method for masking or screening is precipitation. This process can be used in those cases where the solubility products of some precipitates are very low. When we say the solubility products of complexes or precipitates are low, that means they precipitate out, such kind of complexes precipitate out very easily, even in the presence of EDTA. Such metals can be masked by forming precipitates and remain in the solution in the precipitate form, and the remaining ions can be titrated with EDTA in the solution as such. Thank you.